Okay, chapter 6 takes a totally different direction. Laplace transform are applicable in a lot of engineering applications. Section 6.1 is finding the Laplace of every function by definition. 6.2 all the way till the end, till 6.6. We're using tables. We're going to derive the tables in this section. So, this is how it works. Let f of t, which is the function that you are trying to find the Laplace transform for, assuming that t is always bigger than or equal to 0. So some function in which t is always positive. The Laplace transform of this f of t, which we will denote by, that's kind of like Laplace, or we call that f of s. So if you see either the Laplace or simply that symbol, you're really looking at f of s. So the Laplace, which is f of s, is the integral from 0 to infinity of e to the negative st multiplied by this function that you are trying to find the Laplace transform for, dt. Since you are taking the limit as t approaches infinity, from 0 to infinity, you're going to be left with a function of s, and whenever this improper integral converges. So you're only looking at the convergent of it, not the divergent part. So we're going to start with some examples, and I'm adding a bit more to it. So I'm going to start with part D as a practice. D. If I want to find the Laplace of 1, which is f of t, that is, according to this definition, it's right there, it's the integral from 0 to infinity e to the negative st times 1 dt in this case. And I'm not going to work downwards in this case, I'm going to work on a straight line. This is the integral. This is e to the negative st divided by negative s, because I'm integrating with respect to t. As far as t is concerned, s is a constant, right? That is the actual integral. I'm going to evaluate that from 0, t equals 0, to t equal, let's say, a, and I'm going to take the limit as a approaches infinity. That's kind of what we did with improper integrals back in the days. Section 7.8 in calculus, I believe. This is the limit as a approaches infinity of 1 over negative s, because that's a constant, into e to the negative a to the negative sa minus e to the 0. And the limit as a approaches infinity, well, this will approach 0 as long as s is positive. Do we see that? Because that's really 1 over e to the sa. If a is positive, that remains in the denominator, right? And since a is positive, that approaches 0, and I would be left with simply, that's a 1, negative 1 over s times 0 minus 1 will simply be 1 over s. So in this section, we're going to do all the brute force, which is the lengthy problems. And in the next section, all the way through 6.6, we're just going to use a table for this, but we're going to derive those. If I take a and I apply the Laplace on, in part A, f of t, which is t, that is f of s. I forgot to write that up there. You see it's a function of s. That is the integral from 0 to infinity of e to the negative st times, in this case, t dt. So here I need u equal t 1 and 0. dv is e to the negative st. If you integrate, that's negative e to the negative st divided by s. And if you integrate again, that's positive e to the negative st divided by s squared. If you remember that, a plus and a minus. this is going to be the limit as a approaches infinity of negative t over s e to the negative st minus e to the negative st divided by s squared, evaluated from 0 to a, and that is going to yield the limit as I'll write it here. That's the limit as a approaches infinity. If I throw the a in, that's a over s e to the negative e to the sa minus 1 over s squared e to the sa minus, if I put a 0 in, that's a 0 minus 1 over s squared, and the same deal here. Now, as t approaches, as a approaches infinity, I know that by L'Hopital, I have to apply L'Hopital, but the exponential is going to dominate. That's going to be 0. That's going to be 0. And I'm going to be left with simply 1 over s squared. It doesn't show there. And there it is. And if I apply part C, if I apply the Laplace on t to the n, where n is a positive integer, that, oh, I forgot about t squared. I'm sorry, let me do b. b, if I apply the Laplace on t squared, that's f of s, that would be the integral from 0 to infinity of t squared e to the negative st dt. And that would be, and let's see how that works. If I was to go ahead and write u to equal t squared, a derivative, another derivative, and another derivative. And if I was to integrate, and another integral, e to the negative st negative over s cubed. So now it is going to be this. It's going to be oh boy. It's going to be this positive, this negative, and this positive. So that's going to be the limit as a approaches infinity into t squared times 2 e to the negative st divided by s. That's negative. Oh boy. Yeah, third time will be a charm. Negative t squared, okay, minus 2t e to the negative st divided by s squared minus 2 e to the negative st divided by s cubed, evaluated from 0 to a, and I need a bit more space. That's gonna equal the limit as a approaches infinity of negative a squared e to the negative sa divided by s minus twice a e to the negative sa divided by s squared minus twice e to the negative sa divided by s cubed minus, if I throw a 0 in, that's a 0 minus 2 over s cubed. Now, again, you get your wish from pre-calculus, from second semester calculus. Students often ask, do I have to show this? In calculus, you do. Even though a squared is approaching infinity, you apply L'Hopital twice, that's a 0. I forgot the a. that's going to approach 0, and that's going to approach 0. If you're not sure how to do that or how that works, ask me in class. I'll be more than happy in discussing to show you that. And I'm left with a negative 2 over s cubed, and that turns out to be 2 over s cubed. So, and if I move on to part C, if I want to apply the Laplace on t to the n, it turns out to be n factorial over s to the n plus 1. So when I did t to the 0, right, I got 0 factorial over s to the 0 plus 1, which is s. When I did t to the 1, I got 1 factorial divided by s to the 1 more than 1, which is 2. When I did t squared, I got 2 factorial over s raised to the 1 more than 2, which is 3. In general, it turns out if you want to apply the Laplace on t to the n, that is the power factorial divided by s raised to the 1 more than the power. Now, in 6 and 7, use the linearity of Laplace transform to find the Laplace transform of the given function in terms of a and b. Keep in mind, you are only responsible to know 2 of these definitions. This is e to the bt plus e to the negative bt divided by 2. That's all you need to know for this class out of that one section. I believe it's in chapter 8 and 5b, the hyperbolics. Those are the only 2 you need to know. Well, if I apply the Laplace on this, if I take the Laplace applied on the hyperbolic cosine of bt, that would be the integral from 0 to infinity, and e to the bt plus e to the negative bt divided by 2, whatever the function is, multiplied by e to the negative st dt. So, if I really look at this, I'm going to work on a straight path as well. You know what? Let me work downwards, I guess. That is the integral from 0 to infinity. I'm going to take the 1/2 out. When you multiply those, that's e. So if I take e to the bt minus st, I'll factor a t out, b minus st plus e, and when you multiply those, that turns out to be, oops, I already wrote it. That turns out to be e to the negative b plus st all dt. So this is 1/2 times, when I integrate this, this is going to be e to the negative b minus st divided by b minus s, because as far as t is concerned, that's a constant, plus e to the negative b plus st divided by negative b plus s, evaluated from 0 to b and taking the limit as b approaches infinity. And that's going to be 1/2 the limit as b approaches infinity of e. Oh, I used the letter b, I made a mistake. Let's call that a, because b was already there. I didn't pay attention to that. My mistake, I'm bad. B and b. So that's going to be the limit. Oh my goodness, I'm so stuck on b. Let's go with a. A and a. So that would be the limit as a approaches infinity of e. When you plug a in, that is b minus s raised to the a over b minus s. I have a hard time with s, and they chose s out of all of them. Minus e to the negative b plus s raised to the a divided by b plus s minus, if you plug in the 0 for t, that is 1 over b minus s plus 1 minus, because that's a negative right there. I should have wrote it from the beginning, b plus s. And that's going to be 1/2. The limit as b approaches infinity, well, this will approach 0 as long as b minus s is less than 0. If that's negative, that's going to force that down, right? So, as long as that's the case, that will work. And which means as long as s is greater than b. And if s is greater than b here, well, that will be the same, that will be shifted down, that will shoot to 0. So I'm left with 1/2 times negative 1 over b. Actually, let me distribute the negative n. If I distribute the negative n, wouldn't that be 1 over, talking about this, isn't that s minus b minus 1 over s plus b? And if I get a common denominator, wouldn't that be s minus b into s plus b? Wouldn't you multiply top and bottom by s plus b minus s minus b? Wouldn't that be 1 over 2 into s plus b minus s plus b over, isn't that s squared minus b squared? There's a reason why we're simplifying, and I'll show you what that is in the next class session and every session after that. And that would be a b divided by s squared minus b squared. And that's the answer that we want to get. I want to tackle one more, and that concludes this section. Again, this is the longest section. The rest you really have to apply just the tables, which is they do all of this work for you. But in this case, you really want to understand how this works. And here I have a split function. So, wouldn't that be the integral from 0 to infinity of f of t times e to the negative st dt? Well, t is defined, if you run from 0 to 1, that will be t times e to the negative st dt plus the integral from 1 to infinity, and that will be 1 times e to the negative st dt. And I could go to the previous problem and just copy down how this works. This right here would be a negative t e to the negative st. We just did that up in example 4, the very first example we did, minus e to the negative st divided by s, evaluated from 0 to 1, plus the limit as b approaches infinity. This is simply e to the negative st divided by negative s, evaluated from 1 in this case to b. That would be negative 1 e to the negative s over s minus e to the negative s over s minus, when you throw 0 in, that's 0 minus 1 over s, plus the limit as b approaches infinity of e to the negative sb over negative s minus, when you plug the 1 in, e to the negative s times 1 over negative s. And that would be negative 1 over s e to the s minus 1 over s e to the s. Let me see. Yeah, that's right. Plus 1 over s plus the limit as b approaches infinity. this will approach 0 as long as s is negative in this case. Positive, I'm sorry, positive. If s is bigger than 0, then this power is negative. That thing will shoot to the bottom. That will be a 0 plus 1 over e to the negative s. So altogether I have negative 1 over s e to the s minus, of course that's 2 of those, right? Unless I messed up somewhere, plus 1 over s plus 1 over e to the s. Oh, that's not a negative, that's a positive. And let me glance at that. I copied this wrong. If I look at t, that t right there, that's what I should have. This should have been t s squared. So this should have been s squared, s squared, s squared, s squared, right? I'm messing up everything. That should be an s right there, right? Right there. So those two cancel out, and I am left with a 1 over s minus 1 over s squared e to the s. Again, we're getting tables to figure this out. The homework is listed right there.